If we want to understand how we see the world, we have to start here. Without light, the visual world simply doesn't exist. Seeing an object requires a mechanical exchange. Photons must strike a surface and ricochet toward our eyes. Take a highly polished glass mirror and a standard piece of white paper. Which one of these is reflecting light? The paper is reflecting light with the same intensity as the mirror. The difference between a crisp reflection and a blank white page is determined by the specific geometry of that bounce. Physicists categorize this behavior into two distinct types: even, orderly light and uneven, chaotic light. Whether our surroundings appear crystal clear or completely opaque depends on which of those behaviors dominates the surface. To see why, we have to look at the microscopic path of individual rays. Reflection occurs when light strikes a boundary and returns to the medium it came from. This is even reflection. When parallel light rays hit a perfectly smooth surface, they bounce off in unison. Because they remain grouped, they deliver a concentrated image to your eye, allowing you to see your face in a mirror. Now consider a surface that isn't polished, like a standard sheet of paper. At a microscopic level, paper is a landscape of jagged peaks. Parallel rays hit these irregular slopes and bounce away at random angles. The result is a jumbled mess of photons, making it appear as a solid color. Visual clarity is a product of microscopic smoothness. Without that order, light scatters into chaos. While some light ricochets away, other rays penetrate a material entirely. This passage through a medium creates optical tricks, like a pencil appearing snapped in a glass of water, or a coin shifting its position at the bottom of a pool. These shifts are caused by refraction, the physical bending of light as it crosses the boundary between two different transparent materials. This bending is a result of optical density, measured as a material's refractive index. Imagine sprinting across a sandy beach and then hitting waist-deep water. The resistance of the water forces you to slow down. Light experiences a similar change in speed depending on the material it enters. This diagram shows how that speed change forces a turn. When the leading edge of a light beam hits a denser material, that side slows down, while the rest of the beam moves at full speed. This causes the entire path to pivot. If a uniform material causes a predictable bend, we can predict what happens when a medium lacks a single consistent density. Steam rising from a hot cup of tea creates swirling pockets of air with different temperatures and densities. As light passes through these shifting pockets, it encounters constant, varying speed changes, zigzagging unpredictably. Just like a rough surface scatters a reflection, chaotic optical densities scramble light as it travels, distorting the image before it reaches us. We can observe this distortion using a glass jar packed with clear water beads. Any text placed behind the jar is completely unreadable. The jar is filled with hundreds of physical boundaries between the gel beads and the air pockets trapped between them. Light rays frantically zigzag and bend at every single boundary, exiting the jar in a tangled mess. We can eliminate this optical chaos by simply pouring plain water into the jar to fill those air gaps. As water fills the voids, the clear beads vanish, making the background text perfectly legible. Water and these hydrated beads share the exact same refractive index of 1.33. By replacing air, optical speed bumps disappear, and light travels straight, as if through a uniform block. Equalizing the environment's density transforms a chaotic, uneven refraction into a perfectly even, orderly one. Transparency is the result of physics overriding chaos with order. By controlling the speed and trajectory of light, we can manipulate how the world appears to our eyes.